OUTFLOWS, Eagle versus SAMI. So go ahead.
Thanks, Maritza. Thanks for having me here today and giving me the opportunity of talk about my research. For those of you who were at the Cozumel conference, I'm going to repeat a little bit of that and add extra stuff. Before talking about the scientific work, I just would like to mention briefly that I am part of this institution called CASTRO. CASTRO is the Australian Research Council Centre of Excellence for Astrophysics. It's an institution involving 7 universities in Australia, and the aim is to establish Australia as an international leader in wide-field astronomy, and in particular in radio astronomy, because as you know, Australia is huge and is empty, so it's a perfect place for radio astronomy. During the last 6 years, a lot of effort has been made in terms of money, infrastructures, and data analysis, hiring people. And we are now going towards the end of CASTRO, but probably it will get refunded and we will get to a CASTRO 3D, which is the phase 2 of the institution. And there are very good chances that we get refunded because we are doing really well, I would say. And so this is very important for me because, for example, not only they put in place infrastructures like Pathfinder for SKA or other telescopes, but they also improved the way Australia was dealing with a large amount of data. So they created like nodes with very huge supercomputers that I use because I do theory, I run simulations, so it's a perfect place to be right now for running very large simulations. The director is Professor Elaine Sedler, and she's at the University of Sydney, which is the main node of CASTRO, and the other university involved are here. Sydney, Western Australia, Melbourne, where I am, Swinburne, Australian National University, Curtin, and Queensland. Plus we have international partners. Some are Australian, like the Australian Astronomical Observatory. Some others are from abroad, the Max Planck, University of Oxford, and so on. So this is a very huge collaboration, and as I said before, the most important bit of this is the NCI, the National Computational Infrastructures, based in Canberra, where I can run my simulations in the supercomputer they have there. We have a website where you can find information and news, castro.org, and I would like to stress that you can find in the events session this conference. I want to advertise this conference. It will be held in Australia, in Tasmania, Hobart, and it's called The Changing Face of Galaxies. In some sense, it's the continuation of the conference we had last week in Cozumel. So the goal is to explore key physical processes that act to transform and evolve galaxies. All right, let's go back to the talk. The title is Galactic Outflows at Low Redshift, and I'm going to present the work I've been doing using EAGLE simulation, and I will explain in a bit what they are, comparing with SAMI observations, and again, I will talk a little bit about SAMI later on. A list of people involved: Luca Cortez and Chris Power at UWA, my boss, Stuart White. Eating is crucial because he did the observational counterpart of this work. Eating is the principal author of 2 papers, and the work I've been doing is basically the theoretical counterpart of those 2 papers. So during the talk, I will be jumping from observations to simulations because the main topic of my research is trying to reproduce eating data. Rob Crane, and also people from the SAMI and EAGLE teams. All the results will be collected in a paper, which is now in the final stage, is going through the internal review process, so it should be ready soon. All right, a few words about SAMI. SAMI is the Sydney AAO, Australian Astronomical Observatory, multi-object integral field spectrograph, and it is a spectrograph composed of 13 hexabundles. And this is an example of an hexabundle. It's a bundle of fiber optics glued together for a field of view of 15 arcsec. And you can observe, so you can have spectroscopical information, resolved spectroscopical information of a single galaxy, and also you can observe at the same time 12 different galaxies plus one object to calibrate. here is an example of an observation. This is H-alpha velocity, the image of the galaxies from supercosmos, and overimposed is the size of the hexabundle aperture. And here is the velocity map in H-alpha. And here, like, there are different examples. And in some cases, you can see flux. This is the sum of the flux in all the different spaxels. You can see nice disks here or big bulges there. And so this is the instrument we are using to do the SAMI survey. SAMI survey began in 2013, and the goal is to observe almost 3,000 galaxies in different environments. There are different scientific goals for the survey, and the one I am interested in is studying the baryonic cycle, the interplay between inflows and particularly outflows, and the connection between star formation and feedback. Right, this is the range in redshift of the SAMI sample. So redshift here, mass in the y-axis. The red region corresponds to the principal targets, and they cover a redshift range from 0.04 to 0.095, 0.004. And the targets are selected among the gamma 1 field. So we have the principal targets here, while you have secondary targets to cover holes in the observation. And we also have a website there, samisurvey.org, where you can find information and also the data, because we are making public all the data releases. We are now at the 3rd data release. And that's it for the observational part. Now I'm going to spend a few words about EAGLE simulations. And EAGLE is a new set of fully hydrodynamical cosmological simulations. The project is led by Job Shea in Leiden, in Netherlands. And the new thing is that they calibrated the parameters of the simulation to reproduce at the same time, simultaneously, the stellar mass function at redshift 0.1 and the observed mass size relation of these galaxies. This means that those two observable are not a prediction of the simulation. The simulation all the simulations have been tuned to reproduce those. But then there are all the other parameters of galaxies which are real prediction from the simulation. So it's a kind of a different approach than the one that we used before. So you basically tune your parameters to have realistic galaxies, and then you go back and try to recover information and study different properties. From that set, we are using the highest resolution run. It has a box size of 25 comoving megaparsec, and the volume is sampled with 2 times 752 to the cube dark matter and gas particles. It is a Lagrangian code, so you discretize the space, not the mass, like in, discretize the mass and not the space, like in the Eulerian codes. And so you have particles. The mass resolution is 10 to the 5, 2 times 10 to the 5 solar masses, and the spatial resolution is 0.35 physical kiloparsec, which is comparable to the pixel size of SAMI. Among all the different improvements that are in EAGLE, like for example, they have some technical improvements about the SPH algorithm, which is an improved version that allows you to better deal with discontinuities and shocks, which, like, historically they were a problem for SPH code, particle-based code. We have a lot of different physical processes included: cooling, metal cooling, molecular cooling, all different variety of feedback, AGN, stellar feedback, pressure-driven, and so on. But the most important feature is the stellar, for my work, is stellar feedback. AGN feedback is included, but is not relevant for my work, so I'm not going to discuss that. While stellar feedback is implemented thermally, so it means that you have formation of stars in the simulation. When those stars explode, they release energy and they hit the surrounding gas in the ISM. As a consequence, you have the formation of pressure gradients, and naturally, outflows develop. So this means that unlike other state-of-the-art simulations where you have like kinetic feedback in some of them, like the Illustris simulation led by Volker Springel, and in the kinetic feedback you have to specify parameters for the properties of winds. In EAGLE, you don't need to specify any extra parameter. As long as you inject the energy, then the winds develop naturally. There are some caveats in all of this, but the main thing to say is that it's a little bit more realistic than other simulations. So you don't need to specify direction, velocity, mass loading factor with the particles, any of that. But there is not a problem of overcooling. Yes, yes, good point. That's the other thing. We do not switch off cooling. Well, they do not switch off cooling in EAGLE because, well, other simulations, they do that. Or either they switch off cooling or they decouple particles from the hydrodynamic. They do not do this in EAGLE, and they use a trick to do that. So the trick is this one. They store the energy from supernova till the injection of energy creates a jump in temperature, which is high enough to avoid the overcooling. So the jump in temperature in the case of stellar feedback is 10 to the 7.5 K. In the case of AGN is 10 to the 9. So this is the trick that they use. There is a drawback of this, because if you increase the jump in temperature, it means that you need to wait more time to store that energy to get that jump in temperature. And so the feedback becomes a little bit discontinuous. You have a duty cycle. But they made many tests, and this feature is under control. But yes, you're right. So there is this trick to avoid overcooling. Yeah, you have basically you have a density threshold above which you form stars, and you can change the density threshold and change the way you form stars above that density threshold. And all of these parameters are tuned to reproduce what I said before, to reproduce the stellar mass functions. So they did a parameters space study, the parameter space study to define them, and yeah. So I should now stress that we are still talking about a sub-resolution model, meaning that when I talk about stars in this simulation, it's not a single star. It's each star particle represents a simple stellar population because it has a mass of 10 to the 5 solar masses. So we impose an IMF on top of that, and so depending on the IMF, which is Chabrier in my case, we know how much energy goes in a given range of mass, how many supernova you have, but it's all subgrid. We do not explicitly follow all these processes. This is all phenomenological subgrid. The only group right now who is trying to explicitly model the ISM, and they have a resolution that goes down to the molecular cloud, giant molecular cloud, is the FIRE project led by Phil Hopkins. But here we're talking about cosmological simulation, so you have the entire environment. While in the FIRE project, to have such a resolution, you need to get rid of the cosmological environment, and you only model single objects. Otherwise, it would be too computationally expensive. But yeah, that's the way to go for the future. Explicitly model the ISM and star formation processes. This is an example taken from Rob Crane paper in 2015 of the realism of the galaxies. They post-process like this, a cube around the galaxies, creating this fake synthetic SDSS image. And in this paper, they perform the parameter space study that we were talking about before. And like, as you can see, the reference simulation is the best one because it creates like the amount of star formation is spread, is not concentrated like in the other two, the blobs, the blue blobs, but it creates an R50 for these galaxies, which is reasonably similar to realistic galaxies, so to real galaxies. This is phase on, and that's AGN. So starting from that, what I did was extracting unperturbed disk galaxies with like regular disks, no interactions. And we got a final sample of 48 galaxies with stellar masses above 10 to the 10 and low star formation rate. This is a redshift 0. Star formation rate goes from 0.01 to 15 solar masses per year. We then rotate the galaxies, and we get like, we put them edge-on in the XZ and YZ projection. And here you can see an example. In black, you have gas particles, and in orange, stars. And you can see the disks and the nice bulge there. Also in the face-on projection, the big bulge of stars. and this clumpy, complex structure of the gas disk, which is due to the interplay between star formation and feedback processes in the simulation. So on top of these cubes, they are 30 kiloparsec per size. We put a grid of 2 kiloparsec per size and extract velocity maps, basically. So here is, again, an example. And 2 kiloparsec is comparable to the effective resolution of SAMI. I just want to stress here that later on, I'm going to talk about comparison between velocity dispersion or line broadening and in the simulation and in the observations. But we do not include a radiative transfer treatment for this simulation. So we sample the kinematic of gas using the SPH algorithm. Like we take particles and we just count the velocities of those particles. And probably the best way to compare with observation would be to go through a proper radiative transfer treatment. But there are so many unknown to be included on top of simulation that at this stage we thought it wasn't feasible or it wasn't worth it. So we just use, the comparison is between line profiles and kinematic from the SPH, so no radiative transfer. Most importantly, we extract velocity dispersion maps, and velocity dispersion is along the line of sight. So in the XZ projection, you have sigma y, and you can see you have you can see the disk there, and as you move away from the disk, the velocity dispersion increases, which is a good sign. This is what you want. And there might be a hint of environmental effects there because the two, they're not symmetric. Like you have way more dispersion in the positive semiplane, Z semiplane, than in the negative. Yeah.
Are you saying it's a good thing that the velocity dispersion?
I'm gonna tell you why. Because I'm gonna show you right now why. Let me just introduce the observation of Eating. He did a pilot study in 2014 using SAMI, and he targeted a single galaxy at low redshift with outflows, a prototypical disk galaxy. And they performed spectral decomposition of each line, emission line in each spaxel of SAMI. And they used this complicated pipeline. It's called lazy IFU. There should be a paper coming out soon, where they used 3 different components to reproduce the width of the lines and the different features like the skewness there. And those 3 different components are kinematically distinct, and they are one narrow, one intermediate, and one broad. So when you get all the different spaxels, all the different components, you collect all together and you put them in a velocity dispersion plot, which is this thing, is an histogram of the velocity dispersion, you get this. The 3 components sit in 3 distinct regions of the plot. So you have the narrow component here, intermediate, and broad. And in the paper, they argue, Harry, here is the answer to your question, that the low sigma component is mainly due to the disk. So you have H2 regions in the disk associated to star formation, while the broad component is associated to shocked gas and it traces outflows. This is all in the paper. While the intermediate one is kind of in between the two, and it's kind of more complicated to understand the origin. But for us, the 2 importance are disk and outflows. Subsequently, Eating led a paper where we extended the sample, and so we had 40 local edge-on galaxies, and we studied them and we divided them in wind-dominated and non-wind-dominated. And I'll get back later to this. The main thing we started with, it was to test the first connection, low sigma equal to disk, high sigma equal to outflows in Eagle galaxies. So now I'm switching to simulations. This is part of my job. Here is the map. The first simple test we did was to assume a vertical cut and only consider pixels with the coordinate in Z below 1 kiloparsec, meaning that we have only the internal 1 kiloparsec, we are targeting only the disk. And the velocity dispersion distribution is the black line. So it peaks at low sigma and it drops already 100 kilometers per second. While if we take into account the external regions, so if we take into account only pixels outside 1 kiloparsec, 3 and 5, As you move far and far away from the disk, the low sigma component decreases from red to orange, from 1 to 5 kiloparsec targeting region. And he's not very visible here, but the high sigma tail increases. So this is just to establish that we do have this connection. Low sigma is galactic disk, high sigma outflows. And we will start from this. Now, in the 2016 paper led by Ting, we tried to connect properties of wind and properties of galaxies. And we found that it's kind of difficult to connect the two. And so we studied the same thing with Eagle simulations, and we divided our sample in 4 different quadrants, in stellar mass here and specific star formation rate there. The mean is 10.37 in logarithm and minus 10.12 in logarithm for stellar mass and specific star formation rate. So we divided the whole sample in 4 quadrants: low stellar mass with low and high specific star formation rate, Q1 and Q2, high stellar mass, low and high specific star formation rate. And we did the velocity dispersion distribution. Now, it's a kind of crowded plot, but let me guide you through it. Those are the 2 different projections. So this is sigma y, sigma x, but information is exactly the same in the 2 plots. So the first thing to notice is that all the distribution, regardless of where the galaxies are, extend to kind of high velocity dispersion, up to 400 kilometers per second. And according to Ting analysis, this is telling us that in Eagle, if we trust this analysis, the outflows are ubiquitous, are always there, no matter what. The other thing to notice is that galaxies with low mass and low specific star formation rate, they have a more prominent low sigma component. And then when you move to high masses and high specific star formation rate, the distribution, they shift toward higher velocity dispersion. But now we have to discuss the main feature of this plot, which is there is no difference between this distribution. They are all the same. And also at a statistical level, if you do a Kolmogorov-Smirnov test, they are all the same. So this is telling us there weak dependence on standard galactic properties. We tried also the star formation rate surface density, and we divided the sample in low and high sigma star formation rate, the black and the red line respectively. And when you move to high specific star formation rate densities, the distribution moves towards larger velocity dispersion as you expect, and also in agreement with Ting's result. But again, those 2 distributions, they are not different at a statistical level. So at this point, we wanted to dig deeper in the information that we can recover from this kind of test, and we wanted to exploit the predictive power of simulation, because there are other properties that are very easy to measure, to determine in the simulation, if the simulation is realistic enough and you trust them, but they are probably hard to measure in reality, like, for example, the temperature. So we wanted to study the impact of temperature, gas temperature, on the velocity dispersion distribution. This is a prototypical temperature histogram of our galaxies. So you have all the gas, most of the gas is in the disk with cold, let's say cold temperature, 10 to the 4, peaks at 10 to the 4 Kelvin. And you have a tail of hot gas that peaks at 10 to the 6 Kelvin, and that is associated to outflows. So we did this test, and we recalculated the velocity dispersion distribution, imposing the cut that cold particle, only consider cold particle and only consider hot particles, the black and the red. And you can see there is qualitative agreement with the vertical cut we did before when we were targeting the disks. So at a qualitative level, you have that cold particles, they trace the disk, while hot particle, they trace the outflows. I forgot to say, and this is kind of important, then when I established this, oops, no. I spoiled this one. I didn't say that we assumed an additional cut. So when we created these maps, in the positive z semiplane, we only consider particles with positive z velocity, the component of velocity in z positive, and in the negative z plane, semiplane, particles with negative z velocity. So effectively, those particles are moving away from the disk. This is important. Otherwise, this equivalence doesn't hold. Right. So going back, at a qualitative level, we have the same trend. And sorry for this. It's an ugly plot, but it's just to show you that it's true also at a quantitative level. Because when we impose both casts together at the same time, so in the low sigma part here, we are targeting particles with low temperature, and in the disk, so the same pixel, we have exactly the same distribution. And more importantly, when we target particle outside the disk and hot particles, we have exactly the same thing. So this is true at a quantitative level. And at this point, I should say that probably in reality the situation is more complicated because you can have entrainment processes, like you have blob of cold gas entraining, warm diffuse gas outflowing, and that's absolutely true. But at a first order, at least those simulations are telling us that temperature is a good tracer of outflows. Now we're gonna go a step further in this, because so far I talk about outflows, but I didn't specify if those particles are actually escaping the galaxies or they're stopping at some point and coming back. And that is the main thing. What we want to know is what is the amount of gas leaving the galaxy, so galactic winds. And this is again quite simple, fairly simple to do with simulation. So we went back and checked those particles who have velocity below the local escape velocity and particles with velocity above that threshold. And we created the two distribution. And again, slow particles, they create the low sigma component again. And this is very interesting to me. The escaping particles that are leaving the galaxy, they create the high sigma tail. Here you can see we're pushing a lot the analysis because the noise is high, and the amount of particles when you do this selection is low. But still, when it's in agreement, again, qualitatively with the result we found before. And if you do the same exercise we did before, and impose both cut at the same time, you have this interesting thing, that gas particles with high temperature and large velocity are those that create the high sigma tail. And this is to say, probably you get where I'm going, that the equivalence relation we established before are tightened now. So the high sigma component is actually created by galactic winds, which is what you want. So this is telling you that this analysis is in principle very effective in distinguish signature of winds. But as I said before, if you look here, the number statistics is very low. So you probably need better data and better simulation. But it's probably a good way to go. Now, the final thing you can do with simulation is just counting particles, and that's easy to do. And so in that way, we recover the fraction, the minimum fraction of particles escaping the galaxy, which is from very low values, 0.12%, to up to 17% for a mean fraction of 1.4%, which is rather low. But it translates into an amount of ejected mass which is not negligible. It goes from 10 to the 6, roughly, to 10 to the 8 solar masses for a mean ejected mass of 10 to the 7. So this has important implication for the baryonic cycle, because that gas is there, is going out in the IgM, probably polluting the IgM. It will be recycled later on. And so, yeah, this is very interesting to me, also because the minimum amount of mass escaping is not 0. Is greater than 0. So we always have outflows, galactic winds, in Eagle's galaxy. And this confirms what we kind of saw before using the velocity dispersion analysis. But here is just counting particles. So it's a different way to say the same thing. again, if you put it in a different, the same information in a different perspective, you can connect the amount of gas outflowing to the star formation rate and the mass loss rate, if you know the amount of time it takes for a particle to get to the Verida radii. So we did this exercise and we recovered very low loading factor, 10 to the minus 2, which is in agreement actually with the fact that our galaxies have a star formation rate which is rather low, below 15. And it goes up to unity, above unity, for the smallest galaxies, more concentrated galaxies, which is again in agreement with observations and simulations from other groups. Now we're going towards the second part of the talk, where we try to do observationally first. We try to use a more quantitative approach to say if a galaxy has winds, has a prominence of winds or not. Sorry. And what Iting proposed was to use two different parameters to quantify this. The first one is eta 50, and it tells you if a galaxy is a dispersion dominated in the motion of gas, or it is rotationally supported, so it is the fraction between the median velocity dispersion of the spaxel outside one effective radius and the maximum rotational velocity in the disk. And the other parameter is the asymmetry parameter, which basically quantifies how much the extraplanar gas is asymmetric. So you take the velocity map and then you flip it around the major axis of the galaxy, and then you subtract the two and get the residuals. When you don't have winds, the extraplanar gas is not disturbed. So the map, when you flipped it, is rather symmetric and the residuals are low. When you do have winds, the kinematics is disturbed. You don't have very asymmetric profiles anymore, and when you subtract them, you have non-zero residuals outside the disk. So Iting used all of this to try to quantify winds in his galaxies and to distinguish between wind-dominated and non-wind-dominated galaxies, which is what is plotted here actually, the eta 50 velocity dispersion to rotation ratio and the asymmetry parameter. In the first panel you have measurement of the rotational velocity. Here the rotational velocity is measured from the Tully-Fisher relation, so you have a larger scatter. And here is the combination of the two. So the first thing to say is that there's not clear trend between C and eta, even though you would expect some kind of trend. And this has an implication, and I will get back to this later. And Iting assumed a cut, which is he just took those galaxies that he was sure they had outflows, and it says if you are above 0.3 in eta 50, for sure you have outflows. It's phenomenological. I mean, it's not physically based. It's just an observational cut. And if you have galaxies above 1.8 in the asymmetry parameter, those galaxies they have outflow. But again, there's not a clear transition between the two regimes. It seems like there is a smooth transition between non-windy galaxies and wind-dominated. So we did the same exercise with Eagle simulations, and this is the result. There's no clear trend here. The dots, the galaxies are color-coded by the star formation rate surface density, and we have the two projection. And the first thing you can notice is that only a few objects, because we have the two projection here combined, only 3 objects in total are below 0.3 in both the projection. And all the objects, 0.3 in eta 50, all the objects, they have an asymmetry parameter which is above 1.8. So according to this, again, all Eagle galaxies, they have outflows, signature of outflows. The thing is that not even with simulation, which are supposed to be more clean, it should be easier to identify this, the correlation. We don't see a clear correlation. And in fact, when we divided the galaxies by beams of star formation rate surface density, low should be low minus 2.87 in this range, intermediate and high, there's no clear trend. We tried many actually, and the one that works best is when you color code the galaxies by the amount of mass that is escaping, so the galactic wind mass. And when you divide it in bins, you find this, which is way better than that. There seems to be some kind of correlation here when you take into account like bins in galactic wind mass. But this is, I wouldn't say that a correlation is there. I'm not going to oversell this. It can be promising, but at this stage, the correlations are not statistically significant. It might be something interesting to explore, but at this stage, you cannot say anything out of this. So again, this has implication for the interpretation of data. It's fairly early, but I'm going to conclude just by saying that since the highest resolution simulations are so computationally expensive, they only come in a bunch of flavors, let's say, like with 2 different set of parameters, but you don't have an exploration of the parameter space. And specifically, you don't have a higher resolution simulation, highest resolution simulation with no feedback, because it wouldn't make any sense. You would throw away CPU time. And therefore, we couldn't test the methodology, how robust was the methodology using EAGLE simulation. And instead, we used isolated disk galaxies, constrained simulations, where we get the same galactic disk, and it's not meant to reproduce EAGLE galaxies, just to test the methodology. We have the same disk, and we just changed the amount of the strength of feedback included in the disk. So you have no feedback here, weak feedback, fiducial model, and strong feedback. And as you move from left to the right, you see the amount of gas outflowing increases.
What's the parameter you use to regulate this?
Is this thing. It's called the feedback factor. It tells you how much of the energy produced by supernova you are injecting into the surrounding medium. Yeah. It's just that. That's the only thing that changes. And you have the velocity dispersion maps, again, like no feedback. You just have stuff in the disk. And then as you move to the strong feedback, the amount of gas increases on the map. The map is more populated. You translate all of this into the usual velocity dispersion distribution. Here is in a cumulative fraction, and as you want it to be, and as you expected, the no feedback case just produced low sigmas. The largest one is 150, saturates very early. And as soon as you add some feedback, you have distributions that are statistically very different from the one with no feedback. So this is to support the analysis that we have done, and the strong feedback produces the largest velocity dispersion. So to conclude, when you fully exploit the predictive power of simulations, you get that winds are always there. They are ubiquitous in EAGLE galaxies, even though star formation rates are low in our galaxies, simulated galaxies. However, when you try to correlate outflowing activity and galaxy properties, and you try to use observationally based analysis, what you find is very hard to find any signature. So this has implications for the interpretation of data, because our work seems to suggest that probably galactic winds are more common than we think. They're just hard to observe. And so it's a good example on how simulation can be helpful for the interpretation of data, and in particular IFS data. So as I said, the paper is almost done, and so stay tuned for more results to come, and that's it. Thank you.
It's just a technical question. When you derive the asymmetry parameter and you flip the galaxy, you use the position angle morphological one, or the one derived from
That's a very
kinematics?
good question. I have no idea. That's observational base. I'm not sure. I have to check.
Okay.
Sorry.
¿Más preguntas?
Thank you. Good afternoon. So, just the galaxy simulate is only normal galaxies. I think it's not NGN because in the NGN there is other phenomena similar to the outflows. You know about that? So
Yeah.
in this case, in the AGNs, the winds to produce near to the central part, so in the accretion disk.
Mm-hmm.
So my question is there only model to produce these winds in your work as supernova?
Yeah. So yeah, AGN is actually included, but is not actually effective. Well, first of all, because we can just go in the simulation and see how much is the accretion, and they are all quiescent. The second thing is, let me go back. No, I was here. Here. So the box size is small. It's 25 megaparsec. And so you have, you cut the power spectrum to the box size, according to the box size. So the largest object that you have in stellar mass is 10 to the 11. So this means that these are small galaxies. You don't have big clusters. You don't have huge objects. And in this case, even if IGN is there, it's not very effective because, I mean, it's very small according to the stellar mass black hole relation. So it's in there, but we checked that it doesn't play a role. But we want it to be there to make the simulation realistic, even though there are so many unknown in the modeling of AGN. But in our case, no, there is not AGN.
Just a short question and commentary then.
Mm.
The masses you are exploring here are Milky Way sized more or less, yeah? 10 to the something. So in lower masses, I think the winds will be much more stronger, yeah? So in this case, you are just analyzing galaxies where the winds are less effective, let's say, yeah? Because the potential is high. And okay, my more general question, or even philosophical, you know, most of the baryons in the simulations are in the halo, are in the corona, hot corona. So in these galaxies, also is the case for these galaxies, 10 to the something. If the winds are not so strong or are ubiquitous as you are showing, so what is keeping the gas, most of the baryons, in a hot phase in the halo, in the simulations? What do you think is?
That's a good question, and because we specifically target. I mean, we did a test enlarging the size of the cube, and what we found. So you take into account like the other gas, which is supposed to be hot gas or warm gas. And what we found is that this tail goes down, but it is because the I sigma tail goes down. It is because you are dominated by noise. So what I mean for that is that at these scales, when you move far away from the disk, you can probably see it visually. The amount of particles that you have there is low. Like you have 10 particles per pixel, which is really, really low. We are pushing. And so there is up to some point where you get this kind of this transition between what you get close to the galaxy, the sampling, and then what you get outside of the galaxies. And we are not able to sample the transition. So we don't know with this analysis what's going on with the hot gas in the halo. And to answer your question about what creates the hot halo, I think it is mostly accretion. So when your gas accretes from the CGM, it gets shock heated as it gets to the Vira radio of the. Well, here I'm talking about substructures of the
but this is
bigger
for
halo.
clusters, not for
no.
sized halos.
Yeah, in this that's for clusters mostly, but yeah, in this case, good question, because these are all substructures in a bigger halo. So I think it's probably interaction between different, I mean, it's a combination of different things. You have different things going on there. Can be accretion, can be interaction between between galaxies in the same halo. In this case, these are unperturbed, so I do not expect to have a major contribution from that part of the gas, the hot gas in the halo.
Thank you.
Hi. I have two questions, actually. From the observations, I'm sorry, this is an observational question. From the observations, could you say from where in the galaxy is escaping the gas, or is just outflow everywhere?
From the observation.
This is mainly from the bulge or from the disk or from where?
You can say something about it. This is the velocity of the three different components, the velocity map of the three different components I was talking about before. You used to feed the emission lines. So you have the narrow component. It clearly rotates. It creates a pattern. So it's associated. It's everywhere. Actually, it's ubiquitous in the disk, the narrow component. While the transition is hard to say, and it's not very visible here. The broad anyway has a gradient which is 90 degrees tilted. So you have this bipolar outflows coming out. This is what we observe. Probably it's more visible here. So the narrow component comes from everywhere. The broad components, and it only comes from region outside the disk. So that is what we find in this paper.
Okay, so that could be the star formation zones or something like that.
Sorry?
Star formation zones, I mean, H2 regions or something like that, is from there where the gas is escaping, or where the supernova explodes?
I think what supernova is supposed to be, you see it here. The star forming regions are all over the disk. Well, and they can probably see a little bit there. So you can have, as long as you form, you have many supernova and you form bubbles. I mean, it doesn't matter where the original one was, because then you have like the bubbles exploding. But what we are saying that it's kind of tricky, because in the simulation, the star formation happens in the disk, like close to the disk, but the high velocity dispersion arises outside the disk. So it's kind of, let's say, here. You need to, you are dominated by the disk anyway here, even though you can form your bubbles there. You're still dominated by the low sigma component. The rotation dominates, and only when you move far away from the disk in the z direction, then you can have like the contribution. But it does not mean that it arises from outside the disk. That's what you see, and we kind of confirm with the simulations.
Mainly from the halo, anyway.
Yeah.
Something like that. Okay. The other thing is, it's just a comment. When you say wind-dominated galaxies, you are not meaning that the galaxy is evaporating anyway.
No.
Because the
No.
wind is a small part of the galaxy anyway.
Yeah. No. It's like the way Iting defined the two samples. A way to define that you have strong signatures of winds. That's the meaning of wind dominated, and not so strong wind signature of winds. No, it's a small, it's tiny. Yeah, it's 1.4%. That's what we saw. Yeah, it's small anyway. Yeah. So it's a bit misleading. I understand your comment, but yeah, the meaning is like strong wind signatures and no wind signatures. That's the meaning.
In one of your slides, you have a comparison with the constrained isolated simulation. What do you mean with constrained? Are they constrained cosmological initial conditions,
No.
or is?
No. Constrained means it's an isolated disk. You put it there, you put a spin parameter on it, and you let it evolve. There's not a cosmological environment effect whatsoever. That's the meaning of constraint.
Okay. my other question is, you quote a 300 parsecs resolution. Is that the physical resolution? Is that the softening, the SPH kernel?
That's the softening.
Plummer one, spline one?
Proper.
So the physical one is like factor of 2.
Yeah.
Then, do you think that has an impact on the strength of your conclusion?
It does. It does have an impact on the analysis, and that's the reason why we use the pixel size, which are 2 kiloparsec. So it's a factor of how many of that. So we are above the resolution limit of the simulation more than 3 times, which is the usual threshold that you use. But yes, I also, there is another thing to say here. Since this simulation, the parameters depends on the resolution in some sense, and that's the reason why you recalibrate the parameters. I expect that if you increase the resolution, you also have to retune your parameters, and probably the details of the analysis will change, but I do not expect that the main conclusions will change, even though resolution is a big limit here.
Have you tried to compare with zoom-in cosmological
I haven't
simulations?
tried. No, I haven't tried.
That would be.
Yeah, that could be.
I want to make a strong remark here, especially for students. And it's something that we used to say, and it's totally misleading, sorry to say. You say here spatial resolution, and then you quote 0.5 arcsecond. That corresponds to 0.5 kiloparsecs.
Mm-hmm.
This is the sampling, not the resolution. And this is
in SAMI.
in SAMI, and that's totally misleading, because you can make whatever sampling you want. You can put 0.1 arcsecond if you want in an image, and that has nothing to do with the resolution. The resolution of SAMI is the full maximum of the PSF. That is 2.3, 2.4.
Yeah,
and that basically means 5 times larger than that. Okay.
Yeah.
So that's I mean the question that you sample, you can oversample anything if you want, and you are not going to increase the resolution. So take that into account, because the data, the SAMI data at this recife have a physical resolution of 3 to 4 kiloparsecs. Okay.
Yes.
Not 0.5. Okay.
No, yeah. That's the reason why we use 2 kiloparsec here in the beginning. But you're right, especially when it comes to understand this plot. Because here, I'm not smoothing.
Yeah.
And that's something that we have to think about. Also, the way I add the noise, it can be improved, because we don't have like the lazy AFU 1 sigma error like they do. I mean, so there are many things that you can improve.
Yeah.
Specifically, this is still work in progress. You're absolutely right. The first thing I'm going to do is like add a proper treatment of statistical fluctuation, and the second thing is to smooth out. Yeah.
But take care when in the other slide it's written explicitly in the previous one. Explicitly resolution.
Yeah.
And
you got me.
Yeah, it's not the same. Okay.
I was going to ask you about your sample.
Simulator sample?
Yeah, no, the sample you showed. The observational sample. Yeah. Because it's common to have those lanes in these edge-on galaxies. Do you remove those, or what do you do with the objects that have those lanes? It's very common to have them in edge-on.
There is a treatment for dust, yes. I'm sure there is. I don't know the detail of the treatment of dust because I'm not an observer, but anyway. So yeah, there is, the first thing that they do with this lazy IFU, they fit the continuum, they take into account the dust lines, yes, and there is all proper treatment. A paper will appear soon, I think, about this pipeline, which was designed for SAMI data. So everything will be in there. I do know much more do not know much more than. These galaxies? Yes. Yes. Unperturbed, isolated these galaxies. Yes.
Any other question? Okay. Let's thank Edoardo again.
Thank you.
After Paris, don't go.